Now we're going to take some of the stuff that we've learned about waves and apply it to ultrasound in medicine. There are really four main applications of ultrasound in medicine. And so I'm going to describe those. The first one is probably the one that you think of most. This is like, I mean, they do it for a bunch of things, but we're used to seeing pictures of fetuses for checking progress of pregnancies. Whenever waves hit a change in density, and you might think that the key thing here is hitting a higher density material, but in fact, it's true if they hit a lower density material too. But when waves hit a change in density, part of the wave is reflected back. And if you detect that wave, and you measure the time from when it's transmitted to when it's received, and you know the speed of sound through the material being human tissue, you can get a good estimate of the distance away that this change in density is. And so you have an ultrasound device that has two things in it. You have a transmitter that sends a sound wave out into the tissue, and a receiver. And you transmit a wave, measure the time that it takes before it's received, and you use that to measure the distance. How is it that a sound wave is reflected back by a change to a lower density? Well, when you do the first part of the lab this week, think about that. In the lab, we have a transverse wave on a string, and we start out by looking at reflections first where it hits a fixed point. You can think of that as equivalent to like a higher density material that a sound wave hits. And what you see is that the wave is reflected back reversed. But then you also see if the end of the string isn't constrained, it can move freely up and down. That gives a different kind of reflection back. Instead of reversing the wave on reflection, it sends the wave back in the same position that it's in. And it's the same idea with sound waves hitting a lower density material. For our calculations, we're going to use that the speed of sound in human tissue is 1,500 meters per second. That's roughly what it is in water. We're mostly water. And this approach is used obviously in, fetal care. It's also used by surgeons to detect cancers and abnormalities. You can use it in a lot of different applications. The second way that ultrasound is used is that speed of movements happening inside the body can be detected using a Doppler shift. So they detected by measuring the Doppler shift of the reflection. So we know that the formula for the Doppler shift is that the received frequency of a signal is equal to the speed of sound in the material plus the speed of the observer coming towards, and this would be negative if the observer is going towards the source, divided by the speed of sound in the material minus the speed of the source, and that's the source moving toward the observer. That V sub S would be negative in the case that the source is moving away. And then you multiply this by the frequency. Okay, so what represents the speed of the thing that the wave is being reflected off? Well, you can think of that reflection as coming from the source, and so this V sub S in the wave that is detected is the speed of whatever movement in the body you're trying to measure. So this is used, you can do reflections off of blood cells. And that speed can help you find occlusions in blood vessels. You can also do reflections off of things like heart valves and the walls of the heart to see, compare to normal values and look for functioning that way. The third application of ultrasound in medicine is, so if you use higher intensity sound waves, you can provide heating subdermally under the skin to muscles or tendons or things that, that you're trying to rehabilitate. So in this case, we're not worrying about detecting those waves. We're just sending the sound waves in, sending energy through the sound waves into the body, and that energy is being used for some kind of therapy. So higher intensity sound waves are used for subdermal, under the skin, therapeutic heating. And for this application, intensities are in the range of about 10 to 100 kilowatts per square meter. Okay, so a kilowatt is 1,000 watts. So you can also think of this as 10 times 10 to the third to 100 times 10 to the third watts per meter squared. So this is a range where you're going to heat up the tissue, but you're not going to damage the tissue. And then the final application is sometimes in surgical applications, you do want to damage the tissue. You're trying to kill certain tissues. And this is where the highest intensity, let's call this highest intensity sound waves are used. To destroy tissue. And the intensities used here are somewhere in the range of 1 to 40, not kilowatts per meter squared. This time we're talking about megawatts per meter squared. So this is 1 times 10 to the 6th to 40 times 10 to the 6th watts per meter squared. And one thing that you have to consider for all of these cases is that larger wavelengths can be transmitted farther into tissue. For example, that's why whales' sounds in the ocean are very low frequency. That's because that allows them to transmit a lot farther in the ocean. But the size of an object that can be detected is on the order of the wavelength. And so you have to balance these two things. You want to be able to transmit without losing a lot of energy of the wave. So that makes you want larger wavelengths. But you also want a small enough wavelength that you can discern objects at the size, at the resolution that you need. Okay, the calculations we're going to do are all going to be based on things we've done before. So I'm just going to do a couple of sort of similar example problems to what I'm going to ask you to do. And anytime that we're using wave speed on these problems, we're going to use 1,500 meters per second. Okay, so first, we're going to calculate the smallest feature that's visible to an ultrasound receiver and transmitter when the wave has a frequency of 2 megahertz. So that means 2 times 10 to the 6th hertz. And then the second calculation that we want to do is figure out how long does it take in time for an echo to return to the receiver from an object 0.04 meters beneath the skin. So in this case, that's 4 centimeters. Well, for part A, I've mentioned before that probably the most important single equation that goes through all of these wave calculations is the distance equals rate times time equation. By the way, this distance equals rate times time equation, it doesn't work if there's non-zero acceleration. So it only works if there's a constant speed or a constant velocity. So that's one thing. The other thing is you can use the constant acceleration equations to derive this if you just set acceleration equals 0. So that's the connection to the constant acceleration equations. But we're going to use it in the form that the wavelength, that's the distance, is equal to the rate, the wave speed, times the period. And then since the frequency is 1 over the period, we can rewrite this as wavelength is equal to v over f. Okay, and we're trying to calculate the wavelength because, as I said, the size of a feature you can detect is in the ballpark of one wavelength. So wavelength is equal to the wave speed, that's 1500 meters per second, divided by the frequency. We're talking about 2 megahertz, so that's 2 times 10 to the 6 hertz. I wrote it that way just to keep everything in SI units. And we get a wavelength of about 7.5 times 10 to the minus 4 meters. So about 0.75 millimeters. Is that right? Yes, 0.75 millimeters. Second, what kind of time resolution do you need to detect objects, at sort of at the sort of distance scale that's important in these applications? And so I chose 4 centimeters. There are times when you're looking for larger distances, smaller distances. But again, I'm going to use this idea of distance equals rate times time. But this time I'm not going to do it with the wavelength. I'm going to think of that distance as the distance that the sound wave has to travel from the transmitter back to the receiver. And so if the object that it's trying to detect is 4 centimeters away, we have to have the trip to that object and then the return trip from that object. And so you always have to think about the fact that you're doing double that distance with the sound wave. And so we have 2 times 0.04 is equal to the wave speed times the time that we're trying to calculate. And so the time is equal to 0.08 divided by 1500. And that means that this receiver has to be able to differentiate times, somewhere in the ballpark of 5.3 repeating times 10 to the minus 5 seconds. Let me do also an example with the Doppler shift. So in this case, let's say that the Doppler shift is being used to assess cardiac function in a fetus. And we're going to consider an ultrasound frequency of 8 megahertz. And this ultrasound signal is sent to the heart wall. And when the heart contracts, we expect a certain range of velocities from the heart wall to show us that the heart is functioning properly. And then this is reflected back from the heart wall to the receiver. And so remember when you're doing this that the source of the sound, remember that the ultrasound unit is both the transmitter and also the receiver. And so you want to think of it in this case as that wave has already been sent. It's bouncing off of the heart wall in this case, the tissue in the body that's moving, and then coming back to the receiver. So we are going to think of the thing that it's bouncing off as the source in our Doppler shift. And so let's say that the frequency of the received signal is 10 kilohertz, or 10 times 10 to the third hertz, greater than that transmitted signal. And we want to use that to calculate the speed of the heart wall. Well, the first thing we have to do is deal with all these megas and kilos. So we know that the original transmitted speed is 8.0 times 10 to the 6 hertz. We know that the signal that's detected, so I'll call this, so this is our regular F. The detected signal, F prime, is 8.0 times 10 to the 6 plus 10 times 10 to the third hertz. And so that comes out to be 8.01 times 10 to the 6 hertz. And now we can put this into the Doppler equation. The received frequency is equal to the speed of sound through the material, that's going to be 1500, plus the speed of the observer moving towards the source, divided by the speed of sound through the material minus the speed that the source is moving towards the observer. So if the source was moving away from the observer, this V sub s would be negative. And then we're multiplying that by the transmitted signal, so 8.0 times 10 to the 6. And we can then divide both sides by the 10 to the 6 just to make it a little simpler. And so I'm going to divide both sides by 8.0. So we have 8.01 divided by 8.0 is equal to 1500 plus the observer here is the ultrasound receiver, and that's not moving at all, so the top is just going to be 1500. And then the denominator is going to be 1500 minus the speed of the source that we're trying to calculate. And so now I'll multiply both sides by the denominator, and we get 1501.88 is equal to 1500 plus 1.00125 times Vs Now subtract 1500 from both sides, divide both sides by 1.00125, and you get that the speed of the source moving towards the observer is 1.873 meters per second.